I hope people can see my rather plain vanilla slides. So I'm going to assume there's a long enough lag, and I'll just break into it. So yeah, so what am I am talking about the case of staggered interventions when there can be substantial heterogeneity in the treatment effects. And a couple of years ago, just about 2 years ago, I started thinking of, or actually writing down some things. I've been teaching a little bit about regression methods with heterogeneity. And, I thought I had some simple strategies, and I still think they're simple, and I think they're actually fairly useful, and I'll be talking about them briefly. And they're regression methods that extend to nonlinear cases, like when you have a binary outcome and or a count outcome or something like that. But there is this, of course, nice work by Callaway Santana in particular, where they use a kind of long differencing method, essentially looking at lots of pairs of before-after comparisons. And because of the transformation they use, you're able to use other treatment effects type estimators, including things that combine inverse probability weighting and with regression adjustment. So I should say this is work with a current student of mine, Soo-Jiang Lee. It's part of her dissertation. And so we've worked on this together, and I should say I'm not really going to hold her responsible for this presentation. She has her own presentation, which I guarantee looks a bit more sophisticated than this. And in fact, I'm going to show you, unapologetically, I suppose, although I'll probably be a bit embarrassed. Presenting in front of real Stata users is always a bit, dangerous, because my Stata code tends to be simplistic and inefficient. Although I will call on something that Chuck said, which is sometimes just kind of seeing this clunky way of doing it allows you to see exactly what the mechanics of the estimators are. So that'll kind of be my excuse. And these are slides that I created from when I essentially teach this material. Okay, so the question is, so what are we going to do here? So I mentioned, so there's the outline, and I don't have a real empirical example. I have some Stata code scattered throughout the slides with a simulated data set, and then I will show you the results of simulations just before concluding. Okay, so so John just actually mentioned what kind of opened our eyes to this problem of assuming a constant treatment effect, even if we have many treated cohorts. So a cohort, as I'll define formally in a few minutes, is defined by when is the first time period that a unit is subjected to the intervention. Okay, so unit could be a state, it could be a person, it could be a school, and so on. So the unit, I mean the cross-sectional unit, and then of course I'm talking about the case with panel data. So I'm assuming we're observing the same units over time. Okay, so this is the kind of just putting in a treatment dummy which varies over time, ignoring any kind of staggering, ignoring the fact that the treatment may get stronger over time or may get weak, the effect may get weaker or stronger over time. That's a fairly common thing to do. And this, work by these authors and even others basically showed the biases that can arise, in the sense that we may not be estimating anything interesting whatsoever. Okay, so I'm not going to dwell on that. I mean, I'm going to offer positive solutions. So there are lots of recent approaches to this. So Soon and Abraham have a way of doing event study type regressions and then reweighting them so that you make sure that you're in effect not using units that have already been treated as part of the control group, and the Callaway Santana work has been mentioned before. I'm going to call that long differencing with long in quotes, because it may be short differencing because you may be just in adjacent time periods, but as you go further and further past the intervention time, then the differencing becomes longer and longer. So this is the paper that I mentioned. It's still a working paper, where I basically just did kind of the obvious thing that a lot of empirical people, I'm sure, already do, and that is, if you have different cohorts and you have different time periods, then you can just take your treatment indicator and put in interactive effects, with both the cohort and the calendar time, and this allows you to flexibly estimate a sequence of effects. So if you have 6 time periods and a unit is first treated in period 4, then you can estimate effects in periods 4, 5, and 6. And then the next cohort is first treated in period 5, and then you can estimate effects in period 5 and 6, and so on. And so with enough cross-sectional data, you can be pretty flexible about the treatment effects that you can identify. Without a lot of data, you may start imposing restrictions, but it's useful to know that you have the option of being quite flexible with this. Okay, so I don't want to be too snarky about this, but or maybe I do, I don't know. But so when I present that material, I emphasize that the problem is not with the two-way fixed effects estimator. Okay, the two-way fixed effects estimator has its usual great properties. Okay, the problem is we have to apply it to a good model. Okay, so for those of you who may have seen me on Twitter, you probably are tired of seeing this or hearing me say it, but there's a difference between the model and the estimation method, okay? And no estimation method is going to be good if you apply it to a bad model, okay? So I'm going to kind of show you just what the regression is that I have been proposing, and then talk about why Sue and I are looking at something different, okay? Okay, so the benefit of the regression approach is one of the results I was able to show in this paper is when you in fact have linear conditional expectations, and then you add some assumptions. So we don't need no serial correlation or homoscedasticity to hold, of course, for consistency or to do inference. But if they do happen to hold, then the two-way fixed effects estimator, which on this expanded equation is actually the asymptotically efficient estimator. And in fact, it's even the best linear unbiased estimator. So we can actually show that it has a desirable finite sample property. And this question just came up in Chuck's talk, and that is what happens if you do random effects rather than fixed effects. And the two-way fixed effects simply means we're including time effects as well as accounting for cross-sectional effects. Well, as it turns out, in the same paper, I showed that 4 seemingly different estimation methods are actually the same. So two-way fixed effects is the same as a particular pooled OLS estimator, which is the same thing as the random effects estimator applied to the pooled OLS, which is the same thing as an imputation estimator, which uses only the control observations to impute a value for the treated, for the potential outcome in the untreated state for the treated units. And then you use that to create average treatment effects. And to tell you the truth, I wasn't really expecting this a couple of years ago, but all of these estimators are numerically the same. This isn't approximately or asymptotically equivalent. This is numerically the same. Okay, so what about the Callaway Santana approach? If we can do flexible stuff with regression analysis, and I'm not one of those people who rejects regression analysis just because we might want to do something fancier. I'm a big believer in regression analysis, that if we do a careful analysis, we allow enough flexibility, then it can do pretty good things. However, it is true that if the linear model, for example, were to be violated, then we don't really generally know what we're going to be estimating. And so Callaway Santana, because they allow for these doubly robust procedures, they're less efficient. So they're less efficient when the linear conditional mean is correctly specified, but they're going to be more resilient to functional form of the covariates. And moreover, in some simulations I've done, because they don't use all of the information in the control groups, or at least that's not how the current estimators are computed, they have some resiliency to violations of parallel trends as well. Okay, but so there's this trade-off then. If you go with the regression approach, it can be more sensitive to violation of parallel trends, although it's easy to allow heterogeneous trends in the regression approach. I'll mention that a little at the end if I have time. And so, but there's this clear trade-off between having some robustness to functional form misspecification versus having the most efficient estimator. So what Sue and I have done in this working paper, actually, it's my fault. It's not quite a working paper yet. It's been in my court for a little while, but there should be a version we'll be distributing soon, is we remove pre-treatment averages from the outcome in period T. So I'm going to show you the equations for this, but the idea is really just a variation on the Callaway Santana approach, except that we're looking at using all possible control units and averaging them for any cohort in any time period. And so this just requires that we make sure that when we impose the usual assumptions, we might not like them, but the usual assumptions are the no anticipation assumption, the parallel trends assumption. When we have those holding, then we can show that if we take this kind of moving transformation, this rolling transformation of the data, we can then take this transformed variable and we can apply standard treatment effects estimators. So I got a question earlier today about, what if you like to use matching estimators? I don't think the Callaway Santana paper talks about that, but because we're able to show that once you transform your data, the key is once you transform the data, you get unconfoundedness holding, and unconfoundedness is the key assumption underlying all of the standard treatment effects estimators. Okay, so in other words, we can apply regression adjustment if we want to. We can apply inverse probability weighting, or we can combine inverse probability weighting with regression adjustment to get doubly robust estimators. Or if you like to match either based on the covariates or the propensity score, you're welcome to do that as well. So in other words, you can use your favorite treatment effect estimators once you've done the transformation. Okay, so we wanted something where you could do double robustness and that it uses all of the available control units. So we like to think of this as a middle ground between the regression approach where you just assume the conditional expectations are linear, and the Callaway Santana where you're not using all of the available control groups. Okay, so let's quickly set up the notation. So there's no reversibility here. Okay, so that is an interesting question. I have a student working on that as well. But so there are capital T time periods. We are going to have a control period, at least one control period. If it's 2, 5, 6, all the better. The first unit is treated at time S, which is strictly less than T. Actually, you know what? It could be less than or equal to T. It's not very interesting if S is equal to T, because then you only have one treated time period, in which case, the basic methods work quite well. So there's no reversibility. So this is what I was saying. I've actually studied the reversibility question in the context of the regression analysis, and you can do some things. And then the idea is the staggering is that we have additional treatments up through time, the end of the period. Okay, so I'm going to assume for this talk that there is a never treated group. It turns out that you don't need a never treated group, but you do have to, in some cases, adjust the definition of the parameters that are being identified. Okay, so I'm just going to keep that, I'm just going to set that aside for now. So there's a question on how to define the potential outcomes. And when I wrote my regression paper, I borrowed some notation. Athey and Imbens have a paper where they use this notation. And so the idea is we define cohorts, or so in other words, we define G as a group, if you will, and that indicates the first time period that a unit is subjected to the intervention. And then so we have cohort, which is G, and then we have T, which is calendar time. So we imagine potential outcomes by cohort and by calendar time. Okay, now, one of the things we're going to have to do is restrict when T is actually less than G, so that we're talking about a potential outcome prior to the group being subjected to the intervention. We're going to basically assume that all of those things are the same. Okay, so that's the no anticipation assumption, actually. Okay, so this is like, if you would think about it, the cohort is closely related to an intensity variable because it's essentially the inverse of how long you've been in the treatment. So the earlier G is, the smaller G is, then when we go through time, that means the unit has been subjected to the intervention for a longer and longer time period. Okay, and then there's this notation, which looks a little weird, but it's, you know, again, this is Athey and Imbens and Santana has used this. This is just indicating the never treated state. Okay, and of course, we don't really know if a unit is never treated, but all we know is the unit was never treated up until time period T. Okay, so this would be the same as putting in T+1 here, but that looks even more awkward. So I'm just going to use this YT infinity. Okay, so in fact, what the treatment effects are defined to be is to take the difference in these potential outcomes. So we want to know at calendar time T, what's the difference in the potential outcomes if from first being treated in period G, where G is going to be less than T, and then compare that to the potential outcome in the never treated state. Okay, so notice these treatment effects are indexed by cohort or group G and by calendar time. And we're only going to be able to estimate, so this indexes the cohort. And then once we have fixed the cohort, we're only going to be able to identify treatment effects going forward. So starting at the first treated state and then going forward. Okay, so then we need to define cohort dummies. So this is actually analogous to what Chuck was talking about, which is I like to call, these are indicating whether you're ever treated. So these do not vary over time, whether you were ever treated and what is the first period that you're subjected to the intervention. So this is not the time varying treatment variable. This is just indicating cohort, okay? Okay, so then we're assuming in this talk that there are no, we are assuming that there are units that are never treated, okay? And so being never treated or being in one of these cohorts, these are mutually exclusive and exhaustive. You're in one group and only one group, okay? Each unit is. Okay, so here are the parameters that we hope to estimate. These are the average treatment effects on the treated. So we're looking at the average of these potential outcomes for the cohort, which actually was first subjected to the intervention in time period G. Okay, so there can be a lot of these, and I'm not going to have time to talk about aggregation issues and so on. I will immodestly suggest you maybe look for a short course I'm teaching on this, where over 2 or 3 days we can talk about these issues. But of course, once we know that these are separately identified, then we can aggregate them in lots of different ways. Okay, so there's some interest, a lot of interest in the instantaneous effects. What's the effect in the first treated period? And we can estimate that separately by cohort, but then we can also allow, look at these dynamic effects, which allows us to look at persistence. In fact, maybe the intensity of the effect is initially low, but as the policy is in place, the effect gets larger, and then maybe it dampens out at some point. Okay, again, I'm not going to have time here to kind of go through the calculations and so on that one needs to do, but I find it incredibly helpful. And to use the xt_didreg command, you also need to do this, is to have a time varying treatment indicator. Okay, so the time varying treatment indicator in this case is either going to look like this, all zeros for the never treated observation, or it's going to look like this, where you have zeros followed by ones. So these are the two patterns, but notice this is varying over time, whereas the cohort is not going to vary over time. It's going to be one everywhere, or it's going to be zero everywhere. Okay. Okay, so then the assumptions that this is the no anticipation assumption, and this says that essentially the treatment effects, the pre-treatment effects are equal to zero. So we are going to estimate the real treatment effects where we actually have some treated units under the assumption that there's none of this anticipation, so that there are no systematic differences in the potential outcomes before the treatment actually occurs. If this is a problem, then, well, I'll hold off on that and just, if I have time at the end, and talk about that. Okay. Then there is the parallel trends assumption, which says that in the never treated state, essentially the selection into cohort, so when a unit is first subjected to the intervention, is not systematically related to the trend. Now, it's useful at this point to spend just a moment reminding you, this is the real benefit of having repeated observations, is because if we only had a single cross-section, so suppose we only had time period 1, okay, and then we had the treatment and the control, then we would have to assume that the treatment is unconfounded with respect to the level. And that's, of course, the strongest, not unconfounded, is actually independent of the level. This says that the treatment can actually be correlated with what the outcome would have been in the first time period, but what it's not correlated with is the trend on average, okay, over time. Okay. Okay, and then when we have covariates, these get the no anticipation assumption becomes conditional on X. And then here's one that has received a lot of attention. This is the conditional parallel trends assumption. And what this allows us to do is, instead of requiring the parallel trends assumption to hold across the entire population, we now only require it to hold within subpopulations, where the subpopulations are determined by the values of X. So within each of these partitions, now we're assuming the parallel trends assumption holds. And you can incorporate X's both in regression frameworks, in the Callaway Santana, of course, and in the rolling framework that I'm talking about, hopefully now. Okay, so in a sample, what we can compute is, we can compute the cohort, and I would recommend doing this. We see our X's, and then, of course, this is the usual story about missing data. We only observe the outcome for the, for the cohort that the unit actually belongs to. So this is just that simple way of saying that, look, there are all these potential outcomes, but we only observe the one when this is equal to 1, and everything else then is equal to 0. Okay. Practical issues. Sometimes if you have, high frequency data, there may be some time periods where you have no new entry into treatment. Of course, you're not going to be able to generally estimate a treatment effect for such cohorts, so you just leave them out. Okay, so this is just what I proposed in my working paper. It's been revised a couple of times. It should have been revised a long time ago with some new insights I've had, but who knows, maybe I'll take this as motivation to do that. But but what I showed is so I defined these average treatment effects on the treated. And so what I show in this paper is there's a conditional expectation across time that identifies these parameters. And this regression makes perfectly good sense if you just stare at it for a moment. We include cohort effects. We include the X's, which, by the way, are not changing over time. If somebody wants to ask me about that at the end, I'd be happy to comment on it, but it's tricky to allow time varying covariates, so I'm just going to leave it at that. So I'm not going to consider that in these slides unless somebody asks me about it at the end. We allow separate coefficients for every for every cohort. We also put in a full set of time dummies, okay, and we allow the coefficients on the X's to change arbitrarily across time as well. So above this line here that I'm going to draw, everything here is a control. And then below here, these are the average treatment effects on the treated. And so I've interacted the cohort dummy with the time period. Okay, so I'm starting from the first treated cohort, and then from there I go to all the way to the end of the time periods. These are sometimes called the moderating effects. And somebody asked Chuck about whether you could see the coefficients on the covariates. One of the things I like about this is you're going to be staring at those coefficients, and you can see exactly how the treatment effects vary with the X's. Right, you have it right there. The fact this demeaning by cohort forces the coefficients here to be the average treatment effects on the treated. Okay, so there's a lot of heterogeneity that's allowed, maybe too much. Okay, but we can, we can restrict it. We can restrict those like across. There are various ways to do that by intensity and so on. But I've talked about that in my regression paper and so on. So I'm not going to do that here. Okay, so how do the effects can change by cohort, by calendar time, and by covariates. Very, very flexible. So when you write down this regression, it's a long regression. And I've flipped the order of things. Now everything above here is a treatment effect. Is related to treatment effects, and everything below here is a control. And this time varying variable, it's redundant in this regression for getting the coefficient estimates, but I like to include it because you can then compare this regression with what you would do, what the usual thing to do was, right? Which was to impose constant coefficients across all cohorts and all time periods. And so all of this here would be collapsed to just including a single WIT. And this simply states the obvious that, look, as long as I have some entry in every period, I can estimate a separate treatment effect, okay, for each of the cohort calendar time periods. Okay, so I called this extended two-way fixed effects because the extended is actually referring to the model. It's not referring to the estimator. The estimator is just the usual two-way fixed effects estimator. Okay, so there's an equivalent two-way fixed effects estimator. I showed you the pooled OLS version. When you do two-way fixed effects, everything drops out. Okay, that doesn't change over time. Fernando Rios has coded this up in this command called JWDID. I think those are my initials, but I'm not entirely sure. Okay, so probably a little too much about that, but let me show you what we are doing in this follow-up work. So to try to get something which is doubly robust, we decided to kind of take the Callaway Santana as a starting point, but then see how we could bring in all of the relevant control units in a simple way. So the regression approach, because it is efficient under the kind of standard assumptions, we know that it's using the control groups efficiently. Okay, now of course it's using no anticipation and it's using parallel trends, but so do all these other methods, right? So let me remind you, these are the average treatment effects on the treated. And so what we're doing is we need to compute this expectation for the cohort that's first treated in period G. So this is just a telescoping average. if you match up everything, you'll see everything cancels out until we get this. Why would I write this like this? Well, this term is going to go away by no anticipation, because all of these time periods are, excuse me, are dated prior to the first period of treatment. And so in expectation, this is going to be equal to 0. Sometimes a stronger form of the assumption just sets this equal to 0. Okay, so then we have these other two terms to deal with. And so I'm going to define this variable, which is clearly a transformation. I'm going to call it yt dot g, and it's defined to be the potential outcome for cohort G in period T, where I then go back prior to the intervention, the first intervention, right? So averaging these up to G minus 1, G minus 1 is all of the time periods prior to the intervention occurring for this cohort, okay? So instead of just differencing one observation before the treatment, we're going to essentially say, let's average all of these things. Okay, now, how are we going to then use the assumptions to estimate this? Well, this one is easy to estimate because it is the potential outcome for first being treated in cohort in period G, and we want to average over that cohort. So we actually observe this whenever we need to. And so that is just a straight average. So in period T, we look at the cohort G, we average their outcome, but the outcome is this transformed thing. So for each individual unit in this, in this cohort, we define this. It's kind of a differencing, but it's not really differencing. It's a differencing between the outcome in period T and the average of the outcomes up through period G minus 1. Okay. Okay, so this is the one that's always hard because this is the counterfactual. So we need to estimate the mean of this this transform potential outcome in the untreated state, and we need to estimate it for the cohort that's first being treated in period G. So this is where the conditional parallel trends assumption gets used. So I'm not going to go through the algebra since I clearly have limited time, but if you go through the algebra, what you can show is what we have with parallel trends is we have that once we've conditioned on the x's, then conditioning on first being treated in cohort in time period G is the same as not being treated at all. And so now, of course, this we can estimate precisely when we need to because the infinity here and the infinity here match up. So we just have to do some sort of regression analysis. That would be the obvious thing to estimate this using the never treated group. However, we can do better than that. Okay, so this is the no anticipation assumption paired with the parallel trends assumption. And what the no anticipation assumption allows us to do is not only can we just use the never treated units, we can use the units that are not treated yet. Okay. Okay, so the cohorts, this is where I'm saying. So when we're at time T, so like we have a cohort that was first treated in period 4. Now we're in period 6, and suppose there are still time periods yet to come. If a cohort hasn't been treated by period 6, then they act as part of the control group. Any cohort that's already been treated by period 6 can't act as part of the control group because they've already been treated. That's what the simple two-way fixed effects with the constant effect is doing, is it's mushing those bad controls with good controls. So we're just going to force ourselves to only use the good controls. Okay, and the good controls are the not yet treated units. And this includes, of course, the units that will never be treated, that are never treated in the sample. Okay, by the way, I slipped this in. This strategy works even without a never treated group. It's just that if every unit is treated by the final time period, in effect, that final treated group becomes the control group. Okay, and again, we discuss in our paper how you interpret that when you've imposed no anticipation and parallel trends. Okay, so basically, so the idea is this. I'm going to show you quickly the Stata code and then invite you to go look at it. But so we're in period T, and we're looking at cohort G. Okay, so we define this AT plus 1 as a binary indicator, and it's the sum of all of the cohort indicators in time period T plus 1 and later. So this acts as the control for this cohort in period T. Okay, so we're going to condition on being in cohort G and future and being not yet treated. Okay, so once we condition on this event here, we're leaving out all of the units that have been treated up until this period. And then this, of course, is the treatment indicator. Okay, now here's the key to how all of this works. Once we condition on this subpopulation, then the treatment indicator is unconfounded for this variable, this transformed variable with the dot over it in the never treated state. And what I mean by unconfounded, it means it's conditionally mean independent, conditional on the x's. Okay, so here's why we like this approach, because now we're just going to do a cross-sectional analysis. We've defined our control group. We've defined our treatment group. Now we're just going to focus on time period T, a single time period, and we have this transform variable, and now we can apply any treatment effects estimator we want to. Okay, so this is estimation methods, and we can kind of get through this pretty quickly. So here is the algorithm. So once we have fixed a cohort, okay, so we know that G is like equal to 4, let's say, then we fixed a time period. So T is bigger than or equal to 4, and of course it's less than or equal to cap T. Then we define these variables. So this is for unit I, and it indicates that this transformation is different by cohort. And of course, it differs by time period too. So notice this is all the observed data now. So this is the data that we actually have. We take our outcome on Y in period T, and we subtract off the average up until period G minus 1. Okay. We choose as the control group all of the yet to be treated cohorts. This transformation is done for both the control and the treated units. And this is we can do it for all units, but we're not going to look at this for the units that have already been treated, okay, prior to period T. Okay, so then we condition on this event, and we have this data. So this is a cross section. Okay, this is a cross section, and now we just apply. So all we've done here is this looks just like regular, a regular cross-sectional unconfounded treatment effect problem. It's just that we apply it to this transform variable. Okay, so in the 2-period case, what do we wind up doing? In the 2-period case, it's very simple. This becomes, so when T is equal to 2, this Y dot simply becomes Y2 minus YI1, where this is the time period, okay? So this is what this Y dot variable is, and there's only one cohort, so we might as well just define this to be YI2 dot is equal to that. So we're just applying the standard treatment effects to the first difference between period 1 to 2. Couldn't be easier, right? Okay, so interestingly, there are some algebraic equivalences here. So for example, when you apply regression adjustment to the instantaneous effects, so this is cohort first being treated in period G, it turns out this reproduces the pooled OLS two-way fixed effects estimator that I just talked about, okay? For the dynamic effects, they aren't the same. So these are, since the pooled OLS and / two-way fixed effects estimator is best linear unbiased under the traditional assumptions, we know that these can't be the best estimators under the traditional assumptions. and when I say you see slight differences, they're both unbiased, but one of them is going to be more efficient. Okay, so here's where, since I'm getting low on time, I'm just going to, there's something like probably 12 slides of Stata output here. Okay, so of course, one would want to do this with a loop in general. Like, you wouldn't want to probably do this if you had 10 post-treatment periods or something like that. But I set this up so that there are 6 periods. The treatment is first. There's a generated data set here, is first in period 4. And so notice, so these are the 3 transformations for the first treated cohort. Here are the 2 transformations for the second treated cohort, and then there's only 1 transformation for the final treated cohort. And so for this unit here, we can only use the never treated group as the control group because we're in time period 6. Okay, so here's regression adjustment, and again, in the year 2004, so this is actually 2001 through 2006. Okay, so this indicates first being treated in 2004. I'm using all units as control units because the only unit that's been treated in 2004 is this cohort. Okay, then when I go to 2005 for this cohort, I can't use those units treated in 2005. So I use the cohort yet to be treated in 2006 and the never treated cohort. And so that's gotten by. Hopefully that command is correct. Okay, so you can see, so what I'm getting is the estimated effects are these things here. Okay, so I'm just doing this cross-sectional regression and so on. Okay, so this is again this is the third estimate for the so this is the estimated effect in period 6 for the cohort that's first treated in period 4. Okay, here's the immediate effect for the next cohort, first treated in period 5, and so on. Okay, so this is regression adjustment, but we can apply any of the usual treatment effects estimators. So I'm just going to, again, roll through these so you can just see the logical statements are exactly the same as they were before. Here I decided to do propensity score matching. I only have a single covariate here, by the way. That was so, later I'm going to show you in just a few minutes some output. Okay, so you can go through and look, and here okay, so this is all propensity score matching. Then you can do, oops, what did I do here? Then you can do inverse probability weighting combined with regression adjustment. So this is a well-known doubly robust estimator. You can keep going through it. You can see the estimates, of course, are not the same as the matching, but they're clearly in the ballpark. And so we can do this all the way through, and then one more time, then I said reminder of the sample ATTs. Well, reminder, that was clearly a carryover since I haven't shown them to you yet. So because this is generated data, I actually know what the targets are. Okay, so I'm going to skip over that. You can go back, and so for the realized data, I know what the average treatment effects on the treated are actually realized. Of course, that's not the same thing as the population, but because I generated the data, I know exactly what they are in the sample. Okay, and you can see how close they are. Okay, so I'm really getting short on time, but let me just quickly point out that there's a very similar method, and this is the one I'm going to call the long differencing method. And this basically says to go back one period before the intervention occurs, ignoring what happened up until that time. Because we're ignoring what happened up until that time, if, say, parallel trends or parallel trajectories, as Chuck referred to it as, is violated, this may actually have some resiliency to that. Okay, and I've shown simulations of what happens when parallel trends is actually violated, but I'm not going to do that. I'm just going to say this is the approach that's due to Callaway Santana. So again, you choose a control cohort among the not yet treated or the never treated, and then you condition on, you know, the treated units and the control units, and then you can apply any treatment effect method you want to this transform data. So the Callaway Santana method is programmed up in, again, this user written command that Fernando Rios has kindly created for us. Okay, so when you do this, here these are the coefficients you compare to the first three in the you know, either the regression or the well, I haven't shown you the regression in the treatment effects. Then these are the next two, and then this is the last one. Okay. Now you will see that the standard errors here are notably bigger than when you do the rolling method. And the reason is because the default here is to use the never treated group only as the control. You can see that here. The rolling method I just showed you, it uses all of the available controls via this averaging. Okay, so how do we use time periods way back to period 1? Well, we average, you know, all of the periods up until the period before the intervention first occurs. Okay, so these are the comparable, and we have 6 estimates, 3 for the first cohort, 2 for the second, 1 for the last one. Okay, we're getting there. By the way, this is what happens when you do that long regression that I showed you. Okay, so these are the 6 estimates that you can compare. And you'll see, so the one, you know, that just caught my eye, you get a standard error of 0.57 here. The Callaway Santana standard error is about 0.71. And if you go and compare, you know, all of these, you'll see that these are, sorry, not those 3, these 2, and then these 3, you'll see that they're all bigger than the pooled OLS / extended two-way fixed effects. So I did this via pooled OLS, but if I used fixed effects or if I used random effects, this entire output would look identical, except that I would lose. So by the way, these are the moderating effects. Okay, if you want to know how the treatment varies by x's, you can look at these. There's only one x here. And then these are all the controls here. Okay, so these are all the controls put in a very flexible way. And by the way, here are the sample average treatment effects on the treated. So you can see for this one data set, you're going to find that the pooled OLS is closer than, say, the Callaway Santana is here. Okay, but it's not fair to look at one data set. So in 1 minute, I guess, I'm going to show you these simulations. This is, so that data set I just showed you was one realization of this simulated data. I don't see anything particularly weird about this. This is the share of the never treated group. This is the last treated cohort. The sample size is 500, so that's either large or small, depending on your perspective, 1,000 replications. And so these were all set up so that no anticipation holds, parallel trends holds. The first column, these are the sample average treatment effects averaged across the 1,000 simulations, so they should be very close to the population ones. And you can see that there's no bias to speak of in any of these estimators. Okay, but you'll also see that the pooled OLS is the most efficient. The rolling IPWRA is the second most efficient. So this is, but you can see there are some, you know, inefficiencies here compared with the regression approach. And that's because the regression approach is efficiently using all the controls and the rolling IPWRA is not. We don't fully understand, you know, where it's missing out yet, but in any case, it is. Propensity score methods, you know, they're always less precise, it seems. So, you know, my favorite is this one because it tends to be more efficient and it is doubly robust, right? So this is doubly robust. And then the Callaway Santana, you can see, is sometimes more efficient than the rolling propensity score, and sometimes it's less efficient. The efficiency is actually pretty close. So this uses all of the control groups that we can use, but it does propensity score matching. Okay, and I'm happy to make this all available. In fact, this probably should, well, if it's not available, I'll make it available. Okay, so here is the last slide, I think. Well, maybe not quite. There are some other rolling methods. There's a recent working paper by Deschaise Martin and de Hauteville, and there also is a rolling method, but their method doesn't actually accommodate time varying covariates, and so it's like a fixed, it removes time varying covariates, and so the rolling method, of course, clearly allows those because we're just doing treatment effect estimation. Okay, that's the last, that is not the last slide. Okay, sorry about that. I'll make these do files available. Okay, the bottom line is that's and then these are the concluding remarks. So you can use unit specific detrending instead of this de-averaging, if you will. We can leave gaps between the control and treatment periods if we're worried about no anticipation. And in principle, you could include time varying covariates if they're strictly exogenous. Okay, so even with extra time, I wasn't able to do it. So sorry about that, everyone, and rushing at the end. So I'm happy if there's time for questions, I'm happy to field some.
Well, thanks very much, Jeff. That was an amazing presentation, and it really answered a few of the questions that I had about sort of how your new stuff compares with CSDID. So that was super insightful.
Thank you.
And I guess also I guess a big shout out to Fernando Rios Avila, who's coded this stuff up. Super clever guy, and he's made his stuff available, and I've posted those links on the chat. So if you need to download his routines, I think that's super useful. I'll just there was a question here. I just popping it up from Catherine. Is there a difference between the estimator and the Callaway and Santana method? That was immediately my first question. And I think that's great for Catherine to pose that, with the option to include not yet treated as controls, because the CSDID would immediately want to exclude the not yet treated by default. And so if you were to allow them to come in CSDID, would that still be very similar or identical to what you're doing?
That's a great question. This is something that we need to work through other than by, proving it via Stata. But here's what I think. So there are two reasons why the Callaway Santana approach is inefficient. One is if they only use the never treated group, then they're but the other is they only use the period just prior to the intervention as part of the control. So in other words, if we're in period, if we have 3 or 4 pre-treatment periods, then you can always average those, and that's going to be the control for everything going forward. So you're getting a more efficient estimator of that average prior to the intervention. And so it wouldn't be the same if you add more control units and you still use just the time period just prior to the intervention. That's certainly going to improve the efficiency, but it's not going to bring it all the way there.
Got it. Okay, well, there's now a nice flow of, that was an excellent answer, thanks. So Syed Hassan from New Zealand, hopefully it's no longer raining there in Auckland. Will using JWDID, in other words, your ADU as implemented by Fernando, identify the treatment effect when we use log value as the dependent variable, as demeaning is involved in the process?
So thanks for that question. So I'll answer this so when we do linear regression, we know that you can use log of y, you could use the square root of something, you could use anything there, right? And so the answer is this all works. because what you're assuming then, first I'm going to assume that we can take the log and you're not doing something fishy like adding 1 and then taking the log.
Yeah.
But so let's,
Yeah.
okay. So, but then you're assuming that the parallel trends assumption holds in the log. And there are very good reasons for taking the log, right? Because you might be interested in what's essentially a percentage effect, right? So that's a very good idea. But of course, what you're going to do is you're just going to demean the log. So don't make this harder than it is. Create a variable, call it log y if you want, and wherever you saw y, then you just use log y. Let me use this as a way to promote my nonlinear paper, though. If you don't want to take the log, then because maybe you see zeros, you could use the Poisson regression stuff, which works for binary, fractional, and non-negative outcomes. And in the latter case, instead of taking the log, you would just use an exponential functional form and do Poisson regression. Okay.
Great. Thanks, Jeff. I got a question there from Jan Kabatek from the Melbourne Institute.
Hi, Jan.
Jeff,
yeah.
Jeff, could you talk more about how to deal with violations of the non-anticipation assumption? I mean, that's got to be really tough to deal with, given that everyone is going to be anticipating.
It's tough to deal with.
Yep.
So, in a staggered case especially, it's tough, right? Because once the policy is rolled out to some units, then units in other states or whatever, like we have a student who looked at the effects of the body worn cameras, right, that police departments have adopted. And, you have to believe that that's, now the question is, who's paying attention to that? Are criminals actually paying attention to that sort of thing? And I don't know. Of course, the easy answer is to try to allow more gaps between that, but so you only use early periods as the control. That's a little unsatisfying. It's easy to test for it. And actually, I think that's what the Granger causality test is actually testing. And the way we haven't thought about really the best way to do that in this rolling method. In the regression method I talked about, it's really easy. You take that time varying indicator, WIT, and you put it one period into the future in the regression equation. And then, of course, if no anticipation holds, then the fact that policy indicator is flipping in the future should not affect the outcome today. But when you do the test, of course, you want to make sure you allow for enough heterogeneity, because you may reject simply because you don't have enough heterogeneity. I really want somebody to kind of the ways we know. So the no anticipation assumption, when that's violated, that is essentially maps into what we call violation of the strict exogeneity assumption in panel data analysis. And so there are methods of dealing with that if you assume so-called predeterminist or sequential exogeneity. The problem is you have to difference and then look in the past for instruments, and I suspect that's not going to work very well in this setting. So, of course, if you could have an instrument that is strictly exogenous, like it's being randomized or something like that, then that would be one way, I think, to solve it. Okay, yeah, so I see a question by Sasan about unbalanced panels. Yeah, so the rolling approach, we haven't worked through the assumptions under which applying it to an unbalanced panel will work. But I can tell you about the regression approach that I did. If you do two-way fixed effects, then that's going to be the most resilient to having an unbalanced panel, because it's going to allow the unbalancedness to depend on the heterogeneity that you're removing when you do the within transformation. So in that case, when I wrote down that equality pooled OLS is two-way fixed effects is random effects, those equalities break down in the unbalanced case. So in the unbalanced case, you should use two-way fixed effects because it has resiliency to unbalanced panels that the other methods do not. Okay, thanks for that question. Okay, I'll cut the pre-treatment period. Oh, okay, so now you guys are starting to ask, like questions that real empirical people ask. So yeah, these things are hard to implement. I've set this up in kind of an idealized way, right? And that you have this intervention, when it occurs, you have this clean staggered intervention. You don't have any units leaving. So these are all things that those of you who like to dabble in methodology should be thinking about and improving upon from, this sort of talk. But this gives you a tool that, human nature is that when you become a researcher, you don't want to use just OLS anymore, right? So, as an alternative to just, I don't care. I mean, I've been in this business, 40 years or something, and I still, use OLS. But if you want to do something different, then you can do this rolling method and, be careful. You can see how easy it is to implement in using basic Stata commands and, just apply your favorite treatment effect estimator. That way you can say you did some sort of matching. You did a matching difference in differences, and it all works out. And by the way, the common timing case is especially easy with this. Right there's only, there's one timing point, and then you just, take the outcomes after, subtract off the average before for every unit, and then all you have to do is go through each time period to get a pattern of treatment effects. So that's especially easy. And that's the case we start with in our paper, actually.
Oh, really cool. Really cool.
Okay, I apologize to whoever is next on the agenda for taking your time. I tend to talk too much anyway. But thanks for those great questions. Those are really
yeah, fascinating talk, Jeff. Really appreciate it.